Hello and welcome to For the Love of Wisdom, a YouTube channel on philosophy, free thought, and critical thinking. In this video, we're going to begin to learn how to do proofs using the rules of inference. There are an infinite number of deductively valid argument forms. Consider hypothetical syllogism. From two conditionals, we can infer a new conditional with the antecedent of the first and the consequent of the second, so long as the consequent of the first matches the antecedent of the second. We can link a series of conditionals in the same way, such that the antecedent of each matches the consequent of the next, allowing us to infer a conditional with the antecedent of the first and the consequent of the last. Since there is no limit on how many conditionals we can link together in this way, that right there gives us an infinite number of deductively valid argument forms. Or consider constructive dilemma. With any number of conditionals and a disjunctive premise of every antecedent of every one of these conditionals, we can infer the disjunction of all their consequents. This gives us another infinite set of valid argument forms that does not even overlap with the first set. Similar to the infinite set in the constructive dilemma model, there is another infinite set in the pattern of destructive dilemma. And even without counting any of these, there will still be an infinite number of valid argument forms. Of course, it would not be practical, much less even possible, to memorize them all as individual rules. As the number of statements expressed in the premises grew, it would become more and more unwieldy to prove them with truth tables, eventually reaching a size only computers could handle and eventually surpassing that size too. So to show that long arguments are deductively valid, we normally rely on proofs. A proof consists of the application of various rules that are simple enough to be easily recognized as valid and small enough in number to be easily remembered. The rules of inference and the rules of replacement are part of the set commonly used in proofs. If you have viewed my previous videos on symbolic logic, you are now ready to begin learning how to do proofs. In this video, we will begin with proofs that use the rules of inference. Proofs that use the rules of replacement will wait until another video. Before we begin looking at proofs, let's review the rules of inference. We'll start with the rules that use the conjunction symbol, which we're symbolizing with the ampersand here. First, we have the rule of simplification. If we have a conjunction, we can infer either one of its conjuncts through the rule of simplification. And if we have, with the rule of conjunction, if we have two statements on separate lines of our proof, we can conjoin them together with the rule of conjunction. And they could be in either order. We could also infer Q and P from here. And now let's get to the rules concerning disjunctions. Here we have disjunctive syllogism. If we have the disjunction and we have the denial of one of the disjuncts, we can infer the other disjunct from our disjunction. Because if one of them is false, the other one has to be true. And here we have the rule of addition, which allows us to create a disjunction. If we have a true proposition, we can create a disjunction that includes that proposition and any other proposition we wish. Because as long as our original proposition is true, our disjunction will also be true. Our remaining rules concern conditionals. With the rule of modus ponens, if we have the antecedent of a conditional, we can infer the consequent of that conditional. So here we have if P then Q, P therefore Q. And with modus tollens, it tells us if we have a conditional and we have the denial of the consequent of that conditional, then we can infer the denial of its antecedent. With hypothetical syllogism, if we have two conditionals that are linked together with a common term or a common proposition, we can infer a new conditional that has the antecedent of one of them and the consequent of the other one. And here we have the two dilemmas, constructive dilemma and destructive dilemma. These are very similar to modus ponens and modus tollens. They're sort of expanded forms of them. With constructive dilemma, you have a conjunction of two conditionals, and you have the disjunction of their antecedents, and you can infer the disjunction of their consequence. And that's very similar to modus ponens. With destructive dilemma, you also have the conjunction of two conditionals, and you have the disjunction of the denial of their consequence. And you're able to infer from this the disjunction of the denial of their antecedents. And so that's very similar to modus tollens. This is our first example of a proof. And before I continue, I want to make a note of some of the conventions I'm following. We have the expression, the logical expression right here. And to the right of that, I have a couple of slash bars followed by the justification for that line. Here the justification is that it's a premise, and it's the same all the way down. Here I'm following a commenting convention from programming languages like C++ and PHP, where you can make an inline comment after a line by first using this symbol and then following it with your comment. Okay, let's look at our premises here. The first premise is if P then Q. The second is if Q then R. And the third is if R then S. And we want to prove if P then S. And this argument is actually an example of what I was talking about at the beginning of this video. I was giving the example of hypothetical syllogism and how that could be expanded indefinitely to give you an infinite number of logical argument forms, logically valid argument forms. So this is an example of a hypothetical syllogism with three premises instead of just two. You see, if we do a hypothetical syllogism on the first two lines, we would get if P then R, which we could use with if R then S with another hypothetical syllogism to give us if P then S. So let's see what we're doing here. From lines 1 and 2, hypothetical syllogism gives us if P then R. And on line 5, hypothetical syllogism again gives us if P then S from lines 3 and 4. In this second argument, we have two premises. The first premise is P and Q, and the second premise is R and S. And we want to prove Q and S. Well, it looks like all we have to do is simplify each of our premises to get the conjunct that we want for the conjunction we want to prove. And once we have those conjuncts, we can just use conjunction and we have our conclusion. So on line 3, we use simplification to get Q from line 1. And on line 4, we use simplification again to get S from line 2. And now that we have Q and S together, we can use conjunction on line 5 to get the conjunction Q and S, which is what we wanted to prove. In our third example of a proof, we have three premises. The first premise is P, the second is Q, and the third is if the conjunction P and Q, then R. And we want to prove R. Well, it looks like we can easily get R here through modus ponens. All we have to do is get the conjunction of P and Q, which we can easily do from lines 1 and 2 with the rule of conjunction, and we do that on line 4. On line 5, then we get R through modus ponens from lines 3 and 4. In our fourth example of a proof, we have three premises. The first is the disjunction P or Q. The second is the conditional if Q then R. And the third is the conjunction of S and not R. And we want to prove P. With this proof, I want to illustrate a technique I use for doing proofs. And that is to try to go backwards. Let's start with the conclusion we want to prove. That's P. Let's see where P appears in our premises? Well, P appears in the first line in the disjunction P or Q. And we know we can get the disjunct of a disjunction through disjunctive syllogism if we happen to have the negation of the other disjunct. And that would be Q here. So if we can get not Q, we can get P through disjunctive syllogism. Well, Q appears in the second line. If Q, then R. And Q is the antecedent of a conditional here, and we know we can get the denial of the antecedent of a conditional through modus tollens if we have the denial of its consequent. That would be R, and so if we have not R, we can get not Q through modus tollens. And not R appears in the third premise here, S and not R. And we can get one of the conjuncts of a conjunction through the rule of simplification. So that tells us how we can proceed, and we just have to do all of that backwards now. So on line 4 we get not R from line 3 through the rule of simplification. On line 5 we get not Q from modus tollens. From lines 2 and 4 we now have not R, giving us not Q here. And on line 6 we can use a disjunctive syllogism to get our conclusion of P, because we now have not Q, which is denying the other disjunct in the disjunction that P appeared in. We now come to the last example of a proof that we'll be going over in this video. After I go over this example of a proof, I will give you some homework assignments to do. These will be some proofs for you to complete yourself, and there will be another video following this one in which I go over the solutions to those proofs. Okay, so this proof has 5 premises, and the first premise is the conditional if P then Q. The second is the conditional if not P then R. The third is the conditional if S then T. The fourth is the conditional if not S then U. And the fifth is the disjunction of not Q or not T. And what we want to prove is the disjunction of the disjunction R or U or S. The first thing we may look at here is whether our entire conclusion appears anywhere in our premises. And we see it does not appear altogether in our premises. So is it possible to get a part of our conclusion here? We have our conclusion is a disjunction. If we can get one of the disjuncts of a disjunction, we can use addition to get the disjunction itself. So let's see if we can get one of these disjuncts from our premises. How about S here? Well, S appears here in if S then T, and it appears here in if not S then U. Well, it doesn't look like we're able to get S from either one of those premises, at least not with the rules of inference. So let's see what we can do about getting R or U. Well, R appears here as the consequent of a conditional, and U appears here as the consequent of a conditional. And we know we can get the disjunction of the consequence of two conditionals through constructive dilemma if we have a disjunction of their antecedents. So let's look at what the antecedents here are. We have not P and we have not S. If we can get the disjunction not P or not S, then we could use constructive dilemma to get R or U. But is there a way to get not P or not S? Well, not P or not S is the disjunction of the denial of two propositions. And we can get something like that through destructive dilemma. If they appear as the antecedents of conditionals, and we have the disjunction of the denial of the consequence of those conditionals. So let's first see if P and S appear as the antecedents of conditionals. P appears as the antecedent of this conditional, if P then Q, and S appears as the antecedent of this conditional, if S then T. Okay, and let's look at what the consequence of these conditionals are. We have Q and we have T. So we want to get not Q or not T in order to get not P or not S by destructive dilemma. And on line 5, we do have not Q or not T. So that tells us how to proceed. And we just have to do all of that backwards now. So on line 6, first we get the conjunction of the conditionals that were on lines 1 and 3. If P then Q and if S then T. And we're using that with destructive dilemma to give us not P or not S from lines 5 and 6, where 5 is the disjunction not Q or not T, and 6 is the conjunction of the two conditionals. Okay, then on line 8 we can use this with, well, I'm getting ahead of myself here. On line 8 first, we're going to get the conjunction of the two conditionals we want to use with constructive dilemma. And then on line 9, we can use constructive dilemma to give us R or U. And that's from lines 7 and 8, where 7 is the disjunction of the antecedents of these conditionals. 10, I'm going to scroll. And then finally on line 10, I'm going to scroll this up a bit. On line 10, we use addition to give us the conclusion we wanted. The disjunction R or U or S. And now we come to some homework assignments for you. I will not be going over these proofs in the video. I will be doing that in a subsequent video. What I want you to do is try to complete these proofs and then watch the subsequent video where I'll go over the solutions to these proofs. So the first one has 3 premises. The first premise is P. The second premise is if P then Q. The third premise is if Q then R, and you want to prove R. For the second proof, you have 2 premises. The first is P and not Q, and the second is if P then Q, and you want to prove R. You may notice here that R does not appear in the premises at all. And the key to doing this one is that you have a contradiction here. And with a contradiction, you can prove anything. Your task here is to figure out how to do that. The third proof I'd like you to try has 4 premises. The first premise is if P then R. The second is if R then Q. The third is P or T. And the fourth is if the disjunction P or T, then the conditional if T then S. And the conclusion you want to try to prove is Q or S. The fourth proof I would like you to try has 5 premises. The first premise is if P, then the disjunction Q or S. The second is if not Q, then P. The third is if Q, then R. The fourth is not R or T. And the fifth is not T. I'd like you to try to prove Q or S. In the fifth proof I would like you to try, there are 4 premises. The first is P or the disjunction T or R. The second is if U, then not P. The third is the conjunction of the conditional if T then Q and the conditional if R then S. The fourth is the conjunction of W with the conjunction U and V. And what you want to try to prove here is Q or S. The last proof I would like you to try before watching the next video has 5 premises. The first 4 premises are conditionals. The first is if P then Q. The second is if Q then R. The third is if S then T. The fourth is if T then U. And the fifth is the disjunction of not U or not R. And what I'd like you to try to prove here is the disjunction of not S or not P. That concludes this video. Try these proofs out, then come back and watch the solutions video. Thank you for watching.